So thank you very much for the invitation. I'm very happy to be here in person. And as James deviated from hydrates, I'm going to keep going in other direction. I'm going to talk about correlations and unconventional superconductivity and how we can use this for improving and design better superconductor. I'm taking these slides from yesterday's discussion. There were some interesting keywords that I want to highlight. There were the question about should we consider competing orders like spin density wave. There was question about should we look at the non-conventional mechanism. What about electronic correlation? So I'm gonna keep some of these aspects in my talk. Let me start from the including electronic correlation in our superconducting calculation. So if we look at conventional superconductivity, this is emerging, lowering the temperature of a very good superconductor. So there is a very good Coulomb screening, there is a good metal, you lower the temperature and you have the electron-phonon interaction that provide the effective attraction. So for the electron. So in this respect, electronic correlation, competing order and spin density wave are detrimental for superconductivity, at least in general. And the inclusion of this is extremely important because it will lower our expected theoretical critical temperature and will increase the agreement with experiments and improve our predicting power. Can we turn these enemies into our allies somehow? So this is actually where I want to go. I want to talk about unconventional superconductivity. So in unconventional superconductor, I want to mention just two families, cuprates and iron-based superconductor. Superconductivity emerge lowering the temperature in both cases of a very bad metallic phase, characterized by strong electron correlation. The mechanism is a node electron phonon, and pairing is mediated probably by electron collective modes. I don't want to enter in the pairing mechanism because it's not actually the topic of the talk, but just to say that it's not electron phonon and that the metallic state from which we start, it's a very bad metal. So I'm here talking about electronic correlation, possibly spin density wave as a candidate for pairing. And still we have that these are the best families of superconductor at ambient pressure, as you can see from this table. Yes, we are very far from the temperature, critical temperature of our hydrides. But the point is that, as I think Peter yesterday was mentioning, I don't think that room temperature TC would be should be our only focus. I think that have reasonable TC with other important qualities should be reasonably important. So when you study, I have to say I'm not the most brilliant mind that ravel his brain around this problem of superconductivity and strongly correlation, right? But I would say that in the past, an approach that has been popular has been trying to change completely like the view, not adopt the BCS approach, and try extremely something like superconductivity coming from strongly correlation. So I don't want to try that path. I want to try something else. I believe I believe that there is some mechanism for superconductivity that could be, for example, spin fluctuation, maybe combined with some electron phonon. Is not important at the moment. But what I want to see is that this actor playing in a correlated environment are happier or not. So I want to see if the correlation are actually helping and be beneficial for superconductivity. In this sense, in that respect, the strategy to optimize superconductor is going to be the same. I want to see the impact of electronic correlation on density of state close to the Fermi level and on the pairing coupling, and see if I can enhance this aspect playing with correlation. So in this talk, I'm going to focus on the family of iron-based superconductor, and essentially I'm going to touch in detail the first 2 points. So I'm going to show you which kind of correlation we have in the normal state, and highlight which aspect could be potentially important for superconductivity. I'm going to show you the effect of this aspect on BCS-like superconductivity. And in the last part, I'm just let you an overview of what I'm currently doing as a work in progress, in which I'm trying to include more microscopic detail on spin fluctuation mediated superconductivity. A quick overview, I think, is needed, as nobody talked about that in this conference. I'm going to highlight three main aspects of iron-based superconductor. The first one is that it's a multi-orbital system, and the 5d orbital of the iron are very close to the Fermi level, and you need to account to all of them in order to build up a reasonable, in agreement with the experiment, a reasonable best structure. You have different hole and electron-like pockets forming at the Fermi level. And as actually James mentioned, all the families share more or less the same structure with this iron arsenate or iron selenium layer, and the electronic band is quite the same. You have hole pockets and electron pocket at different points of the Brillouin zone. What about the pairing mechanism? So in this band structure, you can see that there is this gamma X and Y pocket that are actually connected by a nesting vector. And this nesting vector is the one that is characterizing the symmetry, the state of the spin density, the magnetic state finding in the undoped compound. So actually the nesting effect is inducing a divergence particular susceptibility at this Q point, and you have that the spin density wave is realized in the undoped system. And when this is perturbed with doping, actually this can provide the effective attraction between electrons, and this interband repulsive spin density wave exchange is actually mediating an S plus minus symmetry pairing, in which the gap on the hole and the electron pockets will have a different sign. In this respect, an open question extremely important is the iron selenium monolayer on strontium, because this is the compound with the highest TC, and is not actually entering in this paradigm because the hole pocket is pretty close but below the Fermi level. So essentially a standard pure nesting mechanism would not work because you have only electron pocket. But I'm gonna talk about that a bit later. Okay. So the last point, I promised there were three. So multi-orbital system, spin density waves are pairing candidate. And the last point I want to highlight is that the normal state, there is a general agreement after this decade that can be theoretically described as a Hund's medal. There is agreement from experiment and theory, and I cannot enter actually in detail and just show you some, for example, fit in which, according to this theory, you will have a strong particle asymmetry around the parent compound. For example, if you dope barium-122 with cobalt and potassium, you can actually achieve experimentally this and explore the phase diagram in that sense. And you see that actually the effective mass follow perfectly the fit. And this is actually quite peculiar of the Hund's medal physics. I don't think that is important. Just believe me, there is agreement that the normal fate can be described by the Hund's medal. I think it's important that I explain to you what the Hund's medal is. So we have to deal with multi-orbital correlated system. This is the standard multi-orbital interacting Hamiltonian in which I'm accounting only for local interaction. So every term is on-site repulsion. And as you can see, I can play a bit and I can reduce this Hamiltonian to a pretty nice expression in which there is a peculiar coefficient. You see this u minus 3j. So for j equal 1/3, it's going to be 0. I want to point out that. There is like the repulsive density term, the Coulomb repulsion. And then you have this J that is the Hund's coupling that essentially wants just to maximize the total spin and the total momentum. What is the physics that came out from this Hamiltonian? So let me start with a case in which I put J almost 0. So essentially I have a collection of multi-orbital correlated system, but the behavior is pretty similar to the standard Mott insulated transition. So you start with a small u, in which you have a well-defined density of state for a metallic state. So it's coherent around the Fermi level. If now I increase, and the other values are important, is the kinetic energy of the system, so the hopping value. And I'm using here as a measure of the kinetic energy, the bandwidth W. So as I increase u, you see that I have mainly two effects. One is the reduction of the kinetic energy of the coherent peak. And this reduction can be encoded in this Z factor, for example, that is a measure of the affecting mass essentially. And the other factor, the other aspect that is changing is that I'm moving spectral weight from the coherent peak to the Hubbard bands. And this, the energy scale that is controlling this is the Hubbard U. You have perfect localization at half filling, the Mott insulating transition. And if you have some doping, you can recover some metallicity. That is bad if you are very close to half filling. So what happens now when J increase? It could change with doping, but it's pretty robust that for any integer filling, imagine that I have 5 orbitals. For 1, 2, 3, 4, except half filling, so 1, 2, 3, 4 electron in 5 orbitals, I have the same physics. This is the plot of the quasi-particle weight, so the coherent, the reduction of the kinetic energy, that with increasing U, you see, I'm plotting different color with different J value. You see that essentially J have 2 different effects. One is that is increasing localization at first, but then is providing a very long U space in the parameter range of a bad metallic phase, in which Z is small but finite. So the critical U at which you have actually the transition to an insulating is very far. So why the metal survives so long? Can we understand that? So a way is that you can plot this zeta curve in a 2D map color plot. So in blue, I'm plotting Z equals 0. So there are insulating phase. And this is a plot of J versus U. Everything is renormalized with the kinetic energy. So you see that you have at high U and small j, the Mott insulating phase. So if you look locally now, you want to avoid double occupancy, and you can have actually on each side 2 electrons. This is the case of 2 electrons in 3 orbitals. You see, you will accommodate 2 electrons in the 3 orbitals, and you have more or less this configuration with the spin randomly orientated because J is not important. If you are on the other side, J want to maximize the spin and the local momentum, as you say. So the best configuration that you can have is accumulating all the electron in some site, leaving empty some other. So this is a typical configuration on the Hund's metal. Why I'm discussing in detail this? Because actually you see that in between these 2 insulating phase, there is this extremely stable and nice metallic state. And this is along this J equal U-third, as I was pointing out before. So what happened? That when you are in between these 2 insulating states, you have a mixture of this configuration. And as you can see now, you can move freely from one side to the other without costing any energy, because the density term is 0 as exactly U-third. So essentially, I think that what is interesting here is that strong correlation effect created 2 very strong insulating phase, but the competition between these 2 phases are creating a very robust metal. You can increase U at this point as much as you want, but the metallic state is extremely stable. The other point that I highlighted before is how the spectral weight is redistributed. So there are a few studies on this, and I prepared this sketch because showing you real spectra could be confusing. But essentially, the message is that while before the redistribution was on energy scale of order U, that is an energy scale of order of electron volt usually, so it's pretty far away from the Fermi level. In the Hund's metal, the energy scale that controls the spectral weight redistribution is much smaller. So essentially, you have a coherent peak that, as I show you, is extremely robust. So the system is metallic at very large U, and this kind of shoulder of spectral weight that is incoherent, but is living very, very close to the Fermi level. So I would say that the main difference in between a low Hund's value and a large Hund's coupling value, close to, for example, this 1/3 value, is that you have a very robust metal in the Hund's metal, and the coherent spectra and the coherent quasi-particle live very, very close in a very narrow energy range. So they are not completely decoupled. Can these 2 aspects be beneficial for superconductivity? I'm gonna show you this looking at a very basic example. So let me consider BCS-like superconductivity. I have a G that is the BCS-like coupling that is constant within a an energy window, and that I will take infinity for now. And I have the electron-electron repulsion that are, encoded in U and J value. And essentially, I'm doing a not self-consistent calculation. I'm taking this electron with the interaction. I'm dressing this electron with some self-energy that I will discuss how I will compute. And then I'm making pairs out of this dressed electron. So I'm solving the BCS equation in which the superconducting propagator has been renormalized with the self-energy of the single particle due to the U and J value. And the way which I can renormalize the electron, of course, I can use different approximation. What I'm going to do is that I'm going to compute with dynamic and mean field theory the full frequency dependent of the self-energy renormalization. And I made the calculation with this, but I also want to check what is the effect of the quasi-particle coherent exactly at the Fermi level. So I'm going to extract at the low frequency the renormalization factor for the kinetic energy Z, and I'm show you result also for this approximation. The model that I'm using, it's a pretty small, minimal model with only 3 orbitals at the Fermi level, but this is enough to reconstruct the essentially the feature of the bands close to the Fermi level and the topology of the Fermi surface. And I'm using, I'm going to show you result for 2 different values of J. You see that these are showing exactly the physics that I mentioned before. For J equals 0 or close to, you have the renormalization of the kinetic energy that go down, and you have a metal insulator transition. For high J, you have this tail and the state remain metallic. So these are the results. I'm computing the gap with the BCS equation. I'm renormalizing the gap using the so we're conducting coupling here for some renormalization factor, and I show you the result for low J and the large J, and I'm using only the Z renormalization factor here. So you see, there is something that may be unexpected. The gap for the Hund's metal is gonna, is dying exactly as the gap for the low J value. So essentially, superconductivity is suppressed by correlation regardless the nature of the correlation. And the fact that you have still a residual Z factor here, so the system is still a bit metallic, is not appreciable, at least in the level of calculation. But what happens if I now take the whole full frequency dependence of the self-energy and I solve the gap in this way? So you see that there are mainly 2 effects. In both cases, you see that the inclusion of full frequency dependence of the self-energy made the superconductivity more robust with respect to the approximation that you have calculated using only the Z factor. And the second aspect is that at the large J, you see clearly that J is boosting superconductivity to survive to very high value of U. So as I told you before, the difference between these 2 states was one, the high metallicity of the Hund's metal that seems not to be important given the previous result on quasi-particle, and the presence of this incoherent state close to the Fermi level. To check if indeed are the states that participate to pairing, what you can do is that you can plot the spectral function. So these are, you see, showing the same characteristic that I mentioned before. For the low J, you have the coherent peak, and then you have these Hubbard bands pretty far away from the peak. And in the case of the Hund's metal, instead, you have a lot of weight accumulated close to the Fermi level. And essentially, you can, I'm showing, yes, result for this line that I'm cutting here. So there is the data for U equal 1 and J small and large. And I can prove better the result if I start to integrate it in the, the BCS integral. I'm moving the cutoff from infinite to closer energy. And you see that essentially the result, I'm plotting here the delta that I obtained with the cutoff at infinity versus the delta that I obtained with the cutoff moving. And you see that the result is stable until 1 electron volt. So it means that integrated over these states that are beyond 1 electron volt is completely irrelevant. It's not changing the value of the gap. But when you are accounting for this incoherent weight, actually the gap is changing. So the main message here is that superconductivity is more robust in the Hund's metal due to the presence of a lot of incoherent weight that is very close to the Fermi level. While the fact that there is a finite Z value, so the density of state at the Fermi level is finite, is not playing a relevant role. This is how far I can get with BCS theory. Of course, there is only this energy scale that is the cutoff. What we are doing now is that we are studying realistic modeling for this, in which I'm considering not a BCS-like superconductivity, but I'm actually introducing a microscopic description of the pairing mechanism. So we are working with Phil D in collaboration with Steve Johnson and Peter to essentially a flex Migdal code. What I mean is that I'm taking into account spin and charge fluctuation via fluctuation exchange approximation. I'm also taking into account the possible presence of electron phonon via self-consistent Migdal approximation. And this is important, especially for the case of iron, selenium on strontium, as I mentioned before. And I'm taking into account a realistic multi-orbital electronic structure using DFT and interacting multi-orbital Hamiltonian. And with respect the current situation, there are several flex code that do more or less the same. The main advantages will be certain of these code are working with very simplistic band model. Other are accounting for the multi-orbital structure of the electronic bands, but are not fully self-consistent. So we want to overcome this limitation and see essentially what is the realistic energy scale of pairing. And this will give us already a qualitative analysis or a qualitative estimate of the interplay that we can have with the Hund metal dynamic properties. And the last step, of course, have to introduce the effect of correlation of this flex Migdal Eliasberg code. That is an open question that would be also important for accounting for electronic correlation in electron phonon system. The only point that I want to, and I'm going to conclude, is that why I believe that including correlation on a flex Migdal code for this iron-based superconductor could be useful and lead to a stronger superconducting mechanism. So I think that this is possible, and my idea, my inspiration come from the alkalido fullerite. So in this system, you have model in which you can include electron phonon coupling, a strong correlation that actually predicted that you would have IRTC with correlation and the phase diagram that you could have with correlation effect. And it's remarkable the agreement between experimental and theory in this case. And why here the effect of correlation was beneficial for superconductivity. Essentially, I'm going to put in simply words, of course, it's more complex than this, but the idea was the superconducting mediators in this system couples to spin and orbital degree of freedom that are not frozen in the Mott insulating phase. What is frozen in the Mott insulating phase are charge fluctuation. So whatever coupling that is, whatever superconducting coupling that is mediated by this, it would be, of course, damaged by the presence of correlation. But the idea is that in iron-based superconductor, the pairing would be mediated by spin fluctuation that are actually not damaged by the presence of correlation. So these are my conclusions. The open question was, can I include correlation effect and see if they enhance the density of state at the Fermi level and the pairing coupling? So the answer is that I show you that the Hund's metal is a robust metal and has a lot of incoherent electron at the low energy. So essentially the answer is that the density of state close to the Fermi energy is higher in the Hund's metal. And this is extremely important and beneficial for superconductivity. So work in progress is to have a realistic and microscopic calculation of the coupling vertex of the pairing vertex. And of course, this is the step we need to answer the second question. Can we have a pairing coupling that is actually enhanced by the presence of correlation? I hope that this will be that I will have answers soon, and I can have, a guidance for material design. The next workshop, I finish with this slide in which I'm thanking all my collaborators, Massimo Capone from CISA, Angelo Valli that was involved in the early phase of the project, and Peter, Steve, and Phil that actually we are putting this effort on this Flex Migdal code. Thank you very much.